Hello everyone, welcome to Engineered Learnings. Engineered Learnings has been created as an effort to help and reach out to all the engineering students, aspirants and professionals out there with the basic understanding and the crux of the topics important for placements, vivas, semesters, competitive examinations and all types of interviews. So let's go to today's topic. Hello everyone, welcome to today's video. So today we are up with another topic of industrial problems relating to fluid mechanics. We have had already two sessions about real life industrial problems where theoretical knowledge meets practical applications. I particularly love these sessions. One of them is about pump priming and the other is about flow meters. Today we will discuss more about a combination of fluid statics and fluid dynamics problems. Coming straight away to the problem that we faced recently in our project that we were given was this. What happened is basically there is a furnace and the feed is coming from top. It's dropping on the furnace and it's undergoing some reaction, and there is a slag bed that is forming and there is a bullion bed that is forming. There is a metal bed and a slag bed, just like it happens in a blast furnace. There is some slag and there is some metal. So let's, for example, let us consider that after the reaction, this is the product phase. So this is my product phase. So it's a liquid phase, and what happens is it's a semi-batch process wherein these holes are closed. There is one siphon here, one hole here to tap out the lead. This is also closed. This is also closed, this is also closed. All the three outgoing points are closed, the inlet points are open. So inlet is continuous, whereas outlet is done in batches, that after 2 hours intervals, the outlets are open, approximately 2 hours intervals. So what was the problem is, as the slag hole was opened, what happened is there are trays fit in the line. So the line is approximately 96 meter in length, and there are trays approximately 560 trays or molds fitted to the rail, and it's a continuously moving railway line. So what happens is one mold gets filled up, next mold gets filled up, mold gets filled up, and like this the slag keeps on filling in these molds. And once the pressure stops coming from inside, the flow is stopped and the hole is closed temporarily. So our problem was that to increase the feed. Now as we increase the feed, the slag formation in those 2 hours will increase, more slag will be formed, more product phase will be formed, and this more product phase will correspond to a higher pressure at the slag tapping hole, and with the higher pressure is associated with a higher flow rate, and with the higher flow rate the problem is the railway line is running at its maximum possible speed of 6 meters per minute. So this is the maximum possible speed of the railway line. So if I increase the tapping speed or tapping flow rate, what happens is there is an overflow of material from the molds. Now primarily this is one of the reasons. Another reason was the metal was getting stuck on the molds. So when it's coming on the return stroke, and getting filled up again after the removal of the metal was not getting completely removed. So some amount of metal was sticking to the surface of the molds, and in its return, what was happening is, since it is now of a lesser volume, it would overflow. But neglecting that problem for the moment, what is happening is that high flow rate due to the increased feed, basically the molds are not being able to tackle that situation. The rail speed is not being able to tackle the situation. Now to change the speed, to change the motor, the entire railway structure is a difficult and a tedious task. So what has to be done in this case? The first thing that one can say is, the thing that strikes your mind is increase the tapping frequency. That is, instead of 2 hours of collecting of slag, increase the tapping frequency. What if the increase of the tapping frequency is not possible due to unavailability of manpower, or maybe due to, if we open this slag tapping hole, there is going to be increased flow and the frequency increases, so there is a continuous exposure of this lance to hot metal, and this lance might be damaged. This particular exit might be damaged. So what if keeping the duration as 2 hours, the duration between the two tappings as 2 hours, how can we optimize the speed such that no overflow occurs? If we know the answer, if you know the answer, pause this video, think about it. If you know the answer, write in the comment section. Write in the comment section. Pause the video. Think about it. I hope you have got the answer. If you haven't, then stay with us till the end of this video. So what we did was, we did a simple calculation. What was the calculation? What is the amount of pressure that this fluid bed above this tapping point is creating on the tapping point? This is the calculation that we did. Now this calculation was not simple because of the fact that here there was a constant suction of gas. The gas that was formed due to the reaction was being constantly pulled out by a suction force. Now the suction is giving a minus 40 kPa pressure. Minus 40 kPa pressure. So around the bed, just above the bed, the pressure is relatively lower than the atmospheric pressure. So the pressure was somewhat minus 30 kPa or minus 20 kPa, which means 101.325 minus 20 kPa, which means 81.325 kPa is just above the bed. So the pressure here is 81.325 kPa. But the pressure at this slag tapping hole exit is atmospheric pressure. So it's 101.325 kPa. Now what we are observing is there's a pressure difference between the 2 points. Now we will have to do a pressure balance. When the slag stops coming out, by itself, what we did is we will have to strike a pressure balance. I'm rubbing this out for a moment, and if we strike a pressure balance, and if I draw this structure like this, this is my bed above the tapping hole supposedly, with the height of h above the tapping hole, what happens is rho gh, this is the pressure of the fluid by virtue of its static pressure, distributed equally on all the sides as given by Pascal's law. Rho gh plus the P1 that is at the top of this, which is hence a negative pressure or like 81.325 kPa, and this pressure is P2. So this is P2. At this condition, the total pressure given by the bed equals the outlet pressure. Now the outlet pressure is atmospheric pressure, so it's P and rho is known, density is known, G is known, height has to be found out. P1 is P atmospheric minus 20 kPa. So we know now we can calculate the value of H. So H is nothing but 20 by rho G. Now we know at the stable condition, what is the height of the bed? Now it will not come. After 2 hours, we know the amount of slag that is formed, the volume of the slag that is formed. Once we know the volume of the slag that is formed, by going with the geometry of the cylinder, horizontal cylinder, we can find out the height it corresponds to. If this much volume of slag is forming in 2 hours, we will find the height of the bed after 2 hours. And that height will be corresponding to this height that was initially there above the bed plus extra height due to slag bed formation in those 2 hours. So that's going to give me the total height. The total volume will be this volume plus the volume that is formed. That will correspond to the total height of the bed from the base, minus the slag tapping hole height will give you the height of the bed above the slag tapping hole. So this is my height of the bed above the slag tapping hole, and this is my tapping hole supposedly. Now from that tapping hole, the liquid will try to come out. Now what will happen is, again we apply pressure balance equation, but this time what happens is we apply it a little differently. We apply Bernoulli here, Bernoulli's equation here. So Bernoulli's equation, if I apply, supposedly this is my bed height, this is my slag tapping hole, this is H supposedly above the slag tapping hole, the bed height, the density is rho supposedly, the pressure at this point is P1, just above the bed is P1, and the pressure at this point is P2. So by Bernoulli's equation we know that P1 by rho G plus V1 square by 2G plus Z1 is equals to P2 by rho G plus V2 square by 2G plus Z2 supposedly, plus a factor of frictional factor of HF, which can hence be neglected here. Let us neglect this for the moment. And what we do is, we know that V1 square, V1, that is just above the bed, since the area is very, very large compared to V2, since the A1 is very large, the velocity, the descending velocity is very, very small, very, very small. So we can consider it for the moment as 0. So considering it for the moment as 0, this V2 square by 2 is nothing but P1 minus P2 by rho G plus Z1 minus Z2, which is nothing but H. So the final equation that comes in is V2 square is nothing but P1 minus P2, that is delta P into 2 by rho plus Z1 minus Z2, that is H into 2G. So this is the formula. So we know delta P, we know the top bed pressure is 80 kPa, the atmospheric pressure is 101 kPa. So we minus that, we know delta P is 20, we know 2, we know rho, we know H, we know G. All known, we find V2. We get V2. Once we get V2, we get Q2. That is the flow rate at the tapping hole. Now what happens is, we know that the speed is like 6 meters per minute. So how many moles, and the total length is 96 meters. So how much time will it take to complete the entire length? 16 minutes. 16 minutes. And in those 16 minutes, 560 moles will be covered. So 560 moles by 16 minutes will give you number of moles that will be passing through a cross section in a particular minute. And each mold has a capacity of 60 kg, which is corresponding to if I divide it by the density, I will get the volume of each mold. So the volume of each mold and the number of molds that is passing, that is the total volume that can be accommodated in that particular minute, and the total volumetric flow rate that's coming in 1 minute. If this exceeds the amount of material that the mold can hold in that particular minute by the virtue of its speed, if this is higher than this, then it will overflow. As we can understand. But what we need to ensure is it doesn't get higher than this. So what we did is, first suggestion was decrease the diameter, the area, the outlet area. So the hole size we told to decrease. Our first suggestion would be to decrease the hole size. Once the hole size decreases, V2 is same, the Q decreases. Q2 decreases. Because we know Q2 is nothing but V2 into A, area of the hole. First suggestion. Second suggestion was, they were tapping from the lower hole, tap from a higher hole. A higher hole tapping, what would it do? It would ensure a lower bed height. It would ensure a lower H. Due to a lower H, a lower V. So use the second hole, upper one to be used such that H decreases and V2 decreases. That is, the height of the slag bed above the tapping hole decreases. The third idea is to fit in a motor such that it is level controlled. So this particular mold will have a level indicator transmitter, LIC, that is a level indicator controller, which will hence control with a final control element, let's CE, the motor speed. Once the level is full, it would push the motor. Once the level is full, it would push the motor. It would activate the motor, it would actuate the motor, and the motion will be continued according to the level. Now, as the bed level decedes, keep on deceding, the speed, the exit speed also keeps on decreasing. Remember that, because the height of the slag bed is slowly decreasing. You see that the final equation of V2 was delta P by rho, something like this, plus Hg. So this H is a factor of time. It's a factor of time. So V2 also becomes a factor of time. With time, V2 decreases. As time increases, V2 decreases. The V2, the liquid flow rate becomes slower as the H keeps on decreasing over time. So thus, at the end, that problem will not occur, overflow problem. The overflow problem will occur at the very beginning when the velocity is very high. So I think that is how you solve a static and a dynamic problem. You'll have to balance how much is coming in from here, how much is going out from there. And we can also increase the tapping frequency. Instead of 2 hours, do it 1.5 hours, so that we can strike a balance, just the optimum balance. That this much is the flow rate at 1.5 hours, and this much is the speed of the conveyor with which it can take this much of volume. So that, I think, will conclude the discussion of the industrial problem for fluid mechanics today. If you liked our video, like it, share it with your friends. We will come up with more exciting and enticing topics in the upcoming weeks. Thank you very much.